Great. I am a graduate student at Columbia University, and before we start today's symposium, let us first begin by acknowledging the indigenous lands from which we are calling in from today. The land that I am calling in from originally belonged to the Munsee Lenape people and is now called Manhattan. The word Manhattan itself comes from a dialect of the Lenape people and serves as a reminder that these lands were stolen. Please refer to the link in the chat to take a moment to reflect on where you're joining us from today. Through the recognition of past harms, we can resolve to create more equitable and humane futures. Now I'm going to pass it off to Mansi to tell us a little bit more about the innovators in cognitive neuroscience.
Thank you, Victoria. Hi, everyone. My name is Manasi Jayakumar. I'm a graduate student at Columbia University. And on behalf of all the students and postdocs on the organizing committee, I would like to welcome you all to today's talk in the Innovators in Cognitive Neuroscience series. Innovators in Cognitive Neuroscience is a collaboration between Columbia University, Dartmouth College, Gallaudet University, Harvard, MIT, Princeton, UPenn, and Yale University. We are devoted to highlighting innovative advances in cognitive neuroscience, particularly from historically underrepresented groups. We acknowledge that these schools are elite institutions of higher learning, and in order to de-silo the generation of knowledge within the ivory tower, we plan to make these talks publicly available with the consent of the speakers, of course. We also provide live closed captioning and ASL interpretation. I will now pass it back to Victoria to introduce our speaker for today.
Great, thanks, Mansi. Before I introduce Iva today, I just want to note that we are testing out the automated closed captioning today. So if anyone does have feedback on the quality of our captions, please let us know by emailing us at innovatorsincognneuro@gmail.com. Okay, great. So let's get started. Today we will be hearing from Dr. Iva Brunec. Iva completed her undergrad at University College London while working with Hugo Spires, and then went on to complete her master's and PhD in psychology at the University of Toronto, where she worked with Morgan Berens and Morris Moscovich. During her doctorate, Iva investigated how different timescales are represented in the brain during naturalistic experience and how these might change with aging. Iva is currently a joint postdoctoral fellow with Nora Newcomb at Temple University and Russell Epstein at the University of Pennsylvania. She's currently working towards understanding the behavioral and neural correlates of successful cognitive map formation and the relationship between ongoing experience and stable long-term representations. Today, Iva will be presenting some of her recent work in a talk titled Behavioral and Neural Dynamics During Navigation, Structure, and Reflect Memory. Iva, we're very glad to have you, and I will hand it over to you now.
Great. Can everyone hear me?
Yep.
Great. Thank you so much to the organizers for inviting me and including me in this series of talks. All the talks in the series so far have been outstanding, and I'm really looking forward to the ones that are yet to come. So thank you. So first, I just wanted to take a second to highlight the advocacy organization that I selected. So this is the National Low-Income Housing Coalition, which is an advocacy organization dedicated to housing justice and aiming to achieve socially just public policy that ensures that people with the lowest incomes also have affordable and decent homes. So I'd like to note that I selected this organization because I assumed that most of the attendees of this talk will be US based, but housing crisis is an ongoing issue everywhere, and there are great organizations fighting for the same cause, which is advocating for affordable and secure housing for everyone by pushing for systemic change. So the reason this is an important issue is that income inequality is a greater issue than ever. 44% of workers aged 18 to 64 are in low-wage jobs, and while not every single one of these workers is at the poverty line, a disproportionate amount is. Extremely low income renters, so renters at the poverty line, account for 25% of all renters. And in Pennsylvania, where I'm currently located, 28% of all renter households are currently considered extremely low income, with a shortage of over 275,000 homes relative to need. In many other states, this distinction is even more severe, with, in some cases, fewer than 30 units for every 100 people or households in need. And it's important to note that the ethnic and racial distribution of households is not even across income categories. So Black, Native American, and Hispanic households are substantially more likely to be extremely low income compared to all households. And this systemic difference in incomes, propped up by discrimination in hiring and wages, is also reflected and exacerbated in housing security, such that these households are disproportionately likely to be extremely low income renters. So the reason that it's that supporting advocacy organizations is important in this case is that this is not a problem of supply, but rather of policy, which can be changed, and we can push for this change. So if we look at the need on the left versus the supply on the right, we can see that in basically every income category, there's a surplus of available units for every income category, except for those who are most in need at the or below the poverty line. So this is why I wanted to highlight a housing justice initiative and organization to push for policies to provide stable, secure, and accessible homes for everyone. So and I invite you to look at some of the excellent work that they're doing and policies they're proposing and supporting. So with that, I'll move on to the scientific part of the talk, which, as Victoria mentioned, is entitled Behavioral and Neural Dynamics During Navigation, Structure, and Reflect Memory. So I'll talk a little bit about some of the work I did during my PhD, as well as some new ongoing work as part of my postdoc. So every day, especially when we were all leaving our houses a lot more, we plan multiple routes that we have to navigate. And this is a problem that we solve every time we navigate anywhere. And it seems trivial while we're doing it, but it's actually a relatively complex problem. So we need to be able to simultaneously represent our current position in space, as well as the goal that we're navigating towards. And as we start our journey, we must continuously update our current location and update our plans accordingly, which involves knowing the distance or time until the next intersection or decision point is reached, and the distance or time until the ultimate goal is reached. So this isn't a problem that becomes solved at any point in time, and so we need to treat it accordingly. It's dynamic, it's continuously changing, we update it on a moment-to-moment basis, and so we should also investigate behavior and brain patterns as they change dynamically. And then there are there's a few key questions regarding this dynamic process. So the first question we can ask is, at what scale do we represent our surroundings and our goals, even when these goals are not necessarily visible? So we need to have multiple scales at which we're representing our environment. And it's not enough to just have a local, immediate representation of one's environment. So this is what I'll be talking about in the first part of my talk, which concerns the scale at which space and time, and as confounded as they are in navigation, are represented. The next question we can ask is, what happens before we have these global representations, or we can flexibly draw on different routes? So how are these global maps built up from moment to moment experience? And specifically, what role do decision points play in forming a stable knowledge of a particular environment? So to effectively encode new routes and new environments that we might not be familiar with, we have to pay special attention to decision points, that is, locations where the direction of travel changes. So it's not enough to so in order to know which way we turn at each location, we also need to know where we're ultimately going, and vice versa. And in the third part, I'll expand zoom out even further from that. So moving beyond knowledge of familiar environments and then beyond knowledge of just individual routes. And I'll be asking the question of how new environments are explored spontaneously to build a cognitive map. So as if we move to a new city or we explore a new environment, we take a number of different routes through that environment, and eventually we build up a sort of internal map of that environment, and we're able to then flexibly draw on different routes that we've learned and recombine these segments into new routes. So how do people approach exploring brand new environments that they've never been in before? This is what I'll talk about in the final part of the talk. So just again as a quick outline or recap. So first, I'll talk a bit about about multiple scales of representation while people navigate in virtual reality. Next, I'll talk about how decision points might be prioritized when learning new routes. And then I'll talk a bit about exploration patterns in new environments. So a lot of the work I'll be talking about today is related to the idea that the hippocampus, as well as many other regions, but the hippocampus supports a cognitive map. So that is an integrated representation of space. So some sort of an internal representation of our surroundings. This idea goes back to the 1970s when O'Keefe and Ostrovsky first reported that on their recordings of hippocampal place cells, they found that as rats roamed around an enclosure, individual cells fired in different locations of that enclosure, giving rise to the notion that the hippocampus provides a spatial code. So in recent years, this work has been extended to spatial and to non-spatial domains, and specific predictions vary by specific theory, but most of them are hippocampus focused, and so I will be hippocampus focused today as well. So in our interest of looking at multiple scales of representation, we turn to the hippocampal long axis. So the hippocampus extends anteriorly to posteriorly in the brain, or ventrally to dorsally in rodents. And one finding that's been reported a few times now, although there's recent work debating how applicable that is in larger environments, is that place field size increases from the dorsal or posterior hippocampus to the ventral or anterior hippocampus. So looking at rodent neurophysiology, in this paper by Kelstrup and colleagues, they reported that spatial autocorrelation, that is the overlap and firing patterns of cell populations, increases from the dorsal to the ventral hippocampus. So this means that in the posterior or dorsal hippocampus, there's very little overlap in the firing patterns, whereas the ventral place cells in the hippocampus tend to cover much larger regions of space. And so there have been parallel findings in humans using functional magnetic resonance imaging, which is also what I'll be talking about today. And in humans in spatial paradigms, the posterior hippocampus was found to represent smaller regions of space or be sensitive to comparisons between nearby locations. And the anterior hippocampus was found to be more sensitive to greater distances of space. So similarly, there's moving into the episodic domain, there's evidence that the posterior hippocampus represents individual episodic elements, such as individual characters or smaller elements of individual events, while the anterior hippocampus supports more integrated global episodic representations. And one important thing, so I'll be staying in the navigational domain for this talk, but one important thing to think about is that in order to accurately think about scales, we have to look at environments that are familiar to participants. So we have to be able to assume that participants are capable of planning realistic routes that they might travel in everyday life. So what we used here was a software designed by Jason Ozupko, who is a former postdoc working with Morris Moscovich and is now an associate professor at SUNY Geneseo. This software allowed us to investigate how participants navigated in environments familiar to them. So this relies on the Google Street View technology. So I'll show you a short video clip of an example route that one might take through downtown Toronto or the university, the campus of the University of Toronto. And hopefully this works. So this is an example of a route. So people were able to look around and use buttons to freely navigate in basically any city that has Street View available, but it also allows us to look at very immersive, familiar environments from a first-person perspective. And from first-person personal experience, it feels very engaging to be able to travel along familiar routes. And in fact, especially now that many or most of us can't see our friends and family and can't travel, this sort of immersion is very welcome. And I just recently noticed this article published in the summer of 2020. And I thought it highlighted nicely just how much humans in general enjoy, how much we enjoy exploring new spaces and wayfinding, as well as revisiting familiar places. So our participants navigated in virtualized Toronto, which was where they had lived for at least 10 years. This work was done in collaboration with many people, but most importantly, co-first author Boudica Balana, who's now a postdoctoral fellow at Johns Hopkins. So we investigated how people's neural patterns changed over the course of navigation in a familiar environment. So participants navigated in 4 different conditions, which I'll explain in just a second, but they basically provided routes, they built the routes up with the experimenter before they were scanned using fMRI. And then each fMRI run was one of these routes. And these routes were very different and depended on each participant. So they were very idiosyncratic, ranging from between 2 to 10 kilometers. So the first 4 routes, so participants were asked to provide 4 routes that they were familiar with, meaning they were familiar with the start location, the goal location, and were told to take the most familiar path between them. The next 4 routes were also familiar. So both the goal and the start were familiar, but the images themselves were left, right, reversed. So participants weren't able to use a simple stimulus response mapping where they could sort of rely on a strategy like, okay, I just have to turn right at that particular Starbucks, making it more navigationally difficult. And then finally, the final 4 routes that the participants provided were so-called unfamiliar routes, where the start and the goal were familiar to them, but they were specifically instructed to take a path that they were less familiar with. And we confirmed that these were the least familiar routes by using a questionnaire. The only category or condition where participants didn't provide the routes themselves was the GPS condition, which was provided by the experimenters. So this was still in the city of Toronto, so there's still some familiarity with the sort of general environment, but the participants weren't very familiar with the start and the goal, and their only task was to follow this dynamic arrow that they could see on the screen. So one way to look at how timescales are represented in the brain is we might predict that if a region is sensitive to longer temporal horizons, the same neural pattern will remain online for a longer period of time. So what we would predict is greater overlap in neural patterns for regions with larger sort of temporal receptive fields or slower temporal drift. And this candidate region for us was the anterior hippocampus. And the way we tackled this approach was to look at temporal, what we're calling temporal autocorrelation. What we are looking at is overlap in neural patterns over time. So we adapted the method of representational similarity to look at the similarity for each pair of adjacent TRs. So what you can see is for every 2 seconds, an image of the entire brain was acquired, and we extracted the patterns for individual voxels from the anterior hippocampus and the posterior hippocampus, and then simply calculated the correlation for each pair of these patterns, and then calculated the average of those correlations. So a higher value here would suggest more pattern overlap over time. So slower representational drift, meaning that the same representation remains online for a longer period of time. So moving on to the results, looking at temporal autocorrelation, as I just described it, we do find that the anterior hippocampus has higher pattern similarity relative to the posterior hippocampus. Now looking at the individual conditions, we see that in both the anterior and the posterior hippocampus, the autocorrelation scales with navigational difficulty as determined by participants' self-report. So here we don't find an interaction between the axes. Both the anterior and the posterior hippocampus show this increase with navigational difficulty. But I will note that there's some ongoing work led by Nicole Bouffard, who's a graduate student co-advised by Morgan Berens and Morris Moscovich, which suggests that there are finer grained differences between these navigational conditions. So that's upcoming. So the second method that we wanted to look at as it relates to the anterior versus the posterior hippocampus was measure we're calling intervoxel similarity. We can, instead of looking at moment-to-moment fluctuations, which is what the measure I just described was looking at, we can also look at how individual voxels relate to one another. So if voxels in a particular region each vary independently from one another, we can interpret that to assume that each voxel carries information in a unique way, so sort of idiosyncratic way. Alternatively, if all voxels in the region co-fluctuate, so they all fluctuate in a very similar manner to every other voxel, we can interpret that to mean that information is carried very similarly. So what we can do is to stack up these voxels, look at their individual time courses, and then calculate the mean similarity between every voxel's time course and every other voxel's time course, which gives us this measure of how redundant the signal is. And redundancy isn't necessarily a negative word here. It can enable greater generalization because there's greater overlap in individual representations. So again, looking at the results, we also find higher intervoxel similarity in the anterior relative to the posterior hippocampus across the entire fMRI run for each root. However, we find no effective condition for this measure, suggesting that there isn't a sort of navigational demand that would modulate the similarity between individual voxel time courses. But that doesn't mean that there's no relationship to behavior. It's just that these two measures seem to tap into different types of behavior. So we also were lucky to have a questionnaire measure designed by Jessica Robin, now at Winterlight, with the intention of measuring participants' reliance on different types of navigational strategies. So some participants, some of us, are very scene-based. So we like to think about places we'll navigate in a scene-by-scene kind of way, and we rely on visual information a lot. Other people might be very map-based, so those participants might never think of individual scenes when they navigate, but rather a bird's eye view or a more abstract map. And of course, there's always a possibility of a sort of mixed representation that might be situation dependent or fully hybrid. And what we find as it relates to this mapping tendency shown here on the x-axis, where higher values reflect greater reliance on map-based strategies, is that lower intervoxel similarity in both the posterior and the anterior hippocampus is actually related to higher mapping tendencies, which would suggest to us that the lower similarity between voxels may enable a more complex navigational strategy with but this measure of mapping tendency had no relationship to temporal autocorrelation. So it suggests that these two different approaches of looking at behavior have different relationships to individual differences in tendencies, strategies, and to navigational demand on a moment by moment basis. So what I've shown here is that the hippocampal long axis, or some evidence that the hippocampal long axis supports a representational gradient. I'd like to mention here that in collaboration with Ida Mamenejad, now at Microsoft Research, we also applied model-based analyses to a subset of these data to reveal that there was a gradient of predictive horizons extending along the posterior to anterior axis of the hippocampus, as well as the caudal to rostral PFC. So Ida gave an excellent talk in this series a few months ago now, describing these results in more detail. And so in the interest of time and repetitiveness, I'm not going to go into further detail, but I wanted to mention this work. And if it seems interesting, Ida has also written a great review explaining the successor representation framework that we applied to this work, to these data in our collaboration. And so, yeah, just as a quick summary, we also, I just wanted to mention again that we find that these signal properties relate to individual differences in navigational demand and strategy. So now moving on to a more to a behavioral question that I also tackled during my PhD. So in the work that I've just presented, we've seen that navigation on familiar routes evokes representations at multiple scales. But what do people pay attention to when traveling along new routes? So beyond looking at places that are highly familiar to people, how do we construct new representations of brand new routes? And here we wanted to look at decision points as key locations of interest. So there's some evidence pointing to the importance of decision points in rodent neurophysiology. And I'll show you a quick animation or a quick cartoon of the real findings using hippocampal recordings, where a rodent is required to do a spatial alternation task. So alternatively take the left versus the right arm. And the recordings of interest are from this decision point, so shown here in the dashed lines. So what the recording suggests is that as the rodent approaches this decision point, sweeps in hippocampal activity are seen extending along both possible arms of the maze prior to the rodent making any sort of a navigational decision. And so this suggests that the hippocampus enables, immediate future states, signals immediate future states, enabling us to evaluate them and then ultimately make a decision about where we're going. So the importance of sequential planning, decision points, has also been highlighted in a few other papers, reinforcing the idea that future planning relies on the hippocampus. So given these results, we wanted to focus on locations that might be most important to remember when navigating a brand new route. So locations preceding turns or these decision points. So moving away from familiar routes, we wanted to control for prior familiarity because of course we don't want any prior knowledge to interfere with representations of space. So we again used our Google Street View approach, but now in an unfamiliar environment, specifically the city of Chicago, and we guided participants along these paths passively. So I have another video here. So this is now a video from this Chicago paradigm, where you'll be able to see that participants were effectively seeing a first-person perspective video, and then at some intersections, the car would pause and then continue. So these would be intersections in the middle of a road segment. Here's one coming up right here. And at other intersections, which is just coming up now, the car would make a turn after pausing. This would be an example of a pre-turn intersection, as you can see here. So this is an example of a turn. I'm hoping the video isn't coming up too choppy, but. So here's in our first experiment, we had participants, we guided participants along this first route, where half of the intersections were preceded turns and half of them were in the middle of road segments. And after guiding participants along these routes a few times, we asked them about their memory for these locations. So we asked them to say for each location to rate their memory. And there were three possible responses. The first one was whether they could re-experience waiting at a particular location, which would mean that they have a very rich, vivid memory of what it was like to stay at a particular location, or whether they know that they had waited at a particular location, or whether it was new. And what we find for the pre-turn intersections, shown here in teal, is that they were significantly more memorable than the mid-segment intersections after controlling for baseline memorability, shown here in the black circles. And one possibility that we were thinking about is that doesn't really address the question of whether it is the locations immediately preceding turns or decision points that are more memorable. It could just be the proximity to a turn, which is a change in visual and spatial context, that's driving these effects. And we also wanted to make sure that this wasn't something specific to this one route. So we built another route also in Chicago. But the structure of the route was somewhat different. For every pre-turn intersection, we also took the location following the turn that was the same distance away from the turn itself. And we again asked participants to provide a response about their memory. And we found that pre-turn intersections were significantly more memorable than the post-turn locations in this case. But we also wanted to look at whether the experience of waiting prior to turning carried more subjective weight. And one way to look at that we thought would be useful is to look at biases in temporal memory or temporal perception. So in this experiment, participants waited for the same exact amount of time at each of these locations, but we showed them pairs of corresponding pre and post-turn locations and asked them to just indicate where they think they had waited for a longer amount of time. So if participants responded on half the trials with the pre-turn location and on the other half with the post-turn location, then their bias would be 0.5. But any sort of bias in either direction would be reflected on either side of this 50% line. And we did find that pre-turn intersections tended to be perceived as longer waits. So each dot here is a participant, and they're color coded depending on their bias and their responses. So as you can see, very few participants tended to report that post-turn locations were where they had waited for longer, and more participants tended to report that pre-turn locations had longer waits. So to us, this was an interesting observation because it suggested that locations preceding shifts in spatial context brought on by turns were more memorable. And this led us to draw this parallel between boundaries in episodic memory and boundaries in space. So in episodic memory, there's a few theories. I cite a small subset here, which differ on the details, but I'll propose that we segment ongoing experience into events based on shifts in perceived context. So in the context of apologies for reusing that word, of films or episodes, of commonly reported observation is that hippocampal signal tends to peak right at the clip offset or at boundaries between individual events. And the magnitude of that peak relates to how much detail gets bound into that episodic representation. While we don't have the corresponding data to directly address this in fMRI in the spatial domain, we have proposed in a sort of more theoretical, zoomed out approach that turns provide structure to spatial memory, the same way as boundaries between events provide structure to our memories. So with a sufficient context shift, each segment or each event is encoded as a separate entity and can be flexibly recombined and retrieved. So what I've shown here is that intersections followed by turns are more memorable than intersections not followed by turns. More broadly, that turns during navigation might play a similar role to that of boundaries between events. So now I'll switch gears a bit, and I'll move away from my PhD work to my current postdoc work with Nora Newcomb and Russell Epstein. So as I mentioned before, a key question is how people approach exploring brand new environments. So we can guide people along new routes, or we can ask them to navigate along routes that they already know, but how do they approach exploring new environments that they've never been in before? And how do we extract, so more broadly, how do we extract structure from our moment-to-moment experience that we can later use to guide future navigation? So one thing we can look at is how people explore. So what their tendency is to explore. And there's this quote that I really like from Harold Gatty's book, Finding Your Way Without Map or Compass, which states, "I don't go far in the beginning. I go some distance and come back again, then in another direction and come back, and then again in another direction. Gradually, I know how everything is, and then I can go far without losing my way." So this quote was from an Australian Aborigine, originally published in this book by Harold Gatty, but I found it in a great book by Michael Bond on finding and losing our way. And I think it captures really nicely how people explore brand new environments. So you need to have some degree of going back and forth, some degree of sort of hypothesis testing and either confirming or disconfirming your beliefs about the structure of the environment that you're in. But what we know is that not everyone successfully integrates information into a cognitive map. So some people are actually very bad at forming a cohesive representation of the environment that they're in. And on a more methodological side, so looking at the data that we already have available, most tasks involve guiding participants along specific routes as the task I was just describing. This isn't meant to be a negative comment about any of these tasks, or they involve retrieving already familiar environments that were learned in real life. Again, going back to the first study I described. There's fairly little data looking at how spontaneous exploration might build up new maps in new environments that were not previously familiar. So we have this data set that was collected by Dr. Jennifer Sutton's lab at the University of Western Ontario, where 84 participants explored this virtual reality environment called Virtual Sulkton. I'll show you a video of one participant's exploration. So the participant is shown here as a blue dot, and their paths will be shown as a red trace. So as you can see here, this participant is very cautious. So they tend to pause quite a bit. And also they retrace their steps. So right here, they turn around, go back. So they retrace their steps, then they pause again, retrace their steps again. And then they pause a bit again before ultimately deciding where they're going to go. So they seem to deliberate quite a few times whether to turn or not, and retrace their own steps. So this is one example of an approach to navigating, which is sped up. So this was about 1.5 minutes in real time. And then I'll show you an example of a different participant whose trace starts at a slightly different location, but they're again shown here as a blue dot. So, oh, excuse me. Okay, so this participant, as you can see, so this is also a brand new environment for this participant, but they don't pause very much, and in the same amount of time, they cover quite a bit more space. So even at turns, so even at these decision points, they don't seem to pause very much, and they just forge ahead without thinking about it very much. So I showed you the same amount of data from both participants, but as you can see, they took very different approaches in how they approach to this exploration task. So another way we can express this is by looking at people's exploration trajectories. So on the x-axis here, I'll show you, I'm showing the time over the course of the experiment, and on the y-axis, the distance covered in each time step, which was 100 milliseconds. And you can see here, this is an example from a randomly chosen participant. that they tend to pause quite a bit every once in a while. So they have these like very slow moving or not moving periods every couple of seconds. But you can see that they started from this sort of middle location in the environment, and going from lighter to darker color is earlier to later in the task. They kind of retraced their own steps a bit. They covered the same streets a few different times, and they intersected with their own trajectory a few times. So this is very different to a different participant, again, chosen largely at random, where they also started in the same location as did all participants. But this person doesn't tend to intersect with their own path very much, or only a few times. And despite starting in the same exact location, they cover a very different area of the space. So if we now just collapse across all participant and plot all of their exploration patterns, we can see that it's there's quite a lot of overlap, but there's also some participants who clearly go off track and try different approaches to exploring. But the key problem that we then came up against is how to describe this complex environment. So it's not a nice grid-like environment, and we didn't guide participants along any particular routes. So it's difficult to describe this environment at first glance. But what we did to try to get around that is to rely on a method that has also been used previously to describe environmental structure, which is space syntax. So this has its roots in architecture, but has also been used in cognitive neuroscience in this really nice paper by Javadi and colleagues, where they used a few different methods, but the one I'll be focusing on is this measure of closeness centrality, or integration, which effectively expresses for every street in a network how topologically close it is to every other street in the network. So the corresponding plot, so for example, these streets in the center of the environment are close to many other streets in the environment, so they have high integration, and these are very far, so they have low integration. And if we now plot virtual Silkton with these same measures, we can see a similar sort of center to periphery pattern, where the streets in the center of the environment tend to be highly connected to, highly close to many other streets in the environment. And this can be plotted in a sort of separate way as in a form of a heat map. So streets in the sort of center of the environment have this warmer color, and those in the periphery have cooler colors corresponding to lower axial integration values. Now, the way we approached describing participants' exploration patterns is we can now take these this like very busy overlapping mess of trajectories, and for each XY coordinate for each participant's trajectory, apply the corresponding axial integration value. So we end up with this plot that basically for every value that is on a path with an integration value, we can calculate the average for each participant of those values. So those participants who tended to stick more in the center of the environment would have higher average experienced integration values relative to those who tend to stick more in the periphery of the environment. So if we plot this experienced integration value on the y-axis over time on the x-axis, we see that all participants, or the majority of participants, move into higher integration areas over time. So it's not the case that some participants, or it's only the case for very few participants, that they just don't find this sort of center of the environment. But the real question is, how does this relate to spatial memory? Is this meaningful in any way, or are we just describing sort of moment-to-moment patterns without any meaningful relationship to memory? So to test spatial memory, participants completed an on-site pointing task where they were placed at each of the 8 buildings in the environment and told to point to every other building in the environment, as well as they were asked to draw a map, which was then fed through the Gardoni map scoring software, which provides effectively a bidimensional regression value between 0, which would mean no correspondence to the actual map, and 1, which would mean very good correspondence to the actual map. So what I'll be showing here is the relationship between experienced integration on the x-axis and the pointing error on the y-axis. So here lower is better because lower error is better performance. And we find a significant relationship between these two. So participants who tended to spend more time in high integration areas had lower pointing error. The same relationship holds for Gardoni scores. So again, participants who spent more time exploring high integration areas had more veridical drawn maps. But one question you might ask is whether this is just a byproduct of the overall coverage of the environment. So it's possible that people just participants who ended up in higher integration areas just covered more of the environment, and then that pulled up their average score. So we also used a different measure of roaming, spatial exploration called roaming entropy. Which has been used in the past as a measure of exploration, and is basically expresses the degree to which one explores the environment in a given amount of time. And so people with higher roaming entropy in their everyday journeys have been reported to have greater subjective well-being. In this really interesting paper where participants' GPS traces were examined. But the way entropy is expressed in space is by dividing the space into quadrants. An example of low entropy would be spending most of your time in one or two of these states, in contrast to higher entropy, where more of the states are covered, even if for a shorter period of time. And these are images from this nice sort of explainer or illustration of how entropy is calculated. So in our example, in our case, we divided the environment into a 50 by 50 grid. So 2,500 possible states. And this is just the coverage across all participants. So these are the trajectories that I was showing a few slides ago, just re-expressed as the number of time points spent in each state. And participants differ in their entropy quite a bit. So this is just a scatter plot. You can see there's quite a bit of range in this roaming entropy measure. And some participants are high entropy, meaning that they tend to explore a lot of new environments with every given time point, whereas others are lower entropy, so they tend to stick to a smaller number of states for longer periods of time. But the very interesting thing is that higher entropy does not relate to this ability to point, nor does it relate to the quality of drawn maps. Sorry. So this is interesting because it suggests that it's not just the coverage. So just covering the environment overall won't necessarily give rise to high quality maps, but that potentially there's something about the strategy or luck about which routes we happen to take that provide structure and scaffolding for more useful cognitive maps. So it's really important to note that these findings apply to this environment. We haven't looked at different environments, which may shape exploration patterns in different ways. And this is something that we talked about briefly in this review paper led by Michael Peer, published last year. And in looking at different environmental structures, we could test whether different exploration measures maybe better describe exploration patterns in different environments or promote different exploration tendencies. So if we express this in the different environments in the form of graphs, this might be one way of looking at that. Lots of work to still be done, but also, of course, it's important to look at at neural activity while people explore. So with that, I'd like to thank everyone involved in this and all of this work, as well as all the funding agencies. And thank you again for including me in the seminar series. And I'd love to hear any questions or comments people might have. Thank you.
Iva, thank you so much for that talk. It was really fascinating. And props to your animations and your figures. They're really impressive and captivating. All right, so we have a number of questions in the chat. So I'm just going to go through them in basically the order that we received them.
Great.
So coming up first, someone is wondering whether the mode of exploration impacts the development of representations in the hippocampus. So for instance, whether you're exploring new spaces by foot or by a car.
Yeah, that's a great question. I think so. It's something that I've talked to a few people quite a few times because, for example, some streets are one ways in the world, and so even in Street View, if you navigate against traffic, it feels kind of jarring because you're not used to seeing it that way if you're driving. So I'm sure that looking at sort of one-way versus two-way environments and looking at these blocked off routes will have an effect. So I'm not too well versed on exactly what kind of hippocampal representation you might expect in one case or another. But if we think of the hippocampus as this sort of more recent successor representation proposal has been thinking about it, which is that it's the distribution of possible future states where one might be that one could navigate to, then I'm sure that if you explore the environment, in a car and some of the streets are one ways, you might not have a sort of bidirectional representation for those locations. But as far as I know, this particular study hasn't been run, although if anyone knows a reference, please post it in the chat.
Great, thank you. Okay, so next up, Leila Davachi is wondering, I think this is in reference to, excuse me, the gradient that we see along the axis of the hippocampus. She's wondering if it's possible that the higher temporal similarity or less granularity means that this region is not being engaged for the task at hand, or in other words, reflects that the noise structure when external or internal information processing is low in that moment.
Yeah, that's also a great question, and we've thought about sort of all the possible explanations for these different temporal scales. One thing that I think is interesting and to us was useful in interpreting this temporal autocorrelation finding was that in conditions with greater navigational demand and that were rated as more navigationally difficult, we found higher temporal autocorrelation. So to us, that sort of spoke to the idea that it was that if you needed to represent more of either your future of where you're navigating and maybe potentially at the same time more of where you've come from to guide your navigation, that would increase that sort of temporal window that you had to hold on to. But because we weren't looking at activation as opposed to sort of a baseline, it's still, it's still up for interpretation exactly how to, what that's reflective of.
Great, thank you. And then just a follow-up question from Leila is, she's curious about whether you find hemispheric differences in this hippocampal gradient.
We do not. There's a few sort of small differences where I think the autocorrelation just in general tended to be a little bit higher in the right hippocampus, if I'm remembering correctly, but nothing. So this is all collapsed across hemispheres because it wasn't a significant factor.
Got it. Thank you. Okay, so next question we have comes from Vasiki Chauhan, and she is wondering if you could please unpack the calculation of mapping tendency that is negatively correlated with intervoxel similarity. She's wondering if this calculation relies on Veronica Bobet's conception of map-based navigation in hippocampal learners and landmark-based navigation in striatal learners.
Yeah, sorry, I didn't spend enough time on that. I went a little bit quickly on that slide. I apologize. So it's a separate questionnaire that's not based on any prior questionnaire. It mostly it reflects, so more positive numbers reflect greater mapping tendencies. And the way it was constructed was more to look at how people tend to report navigating in everyday situations. So there's definitely similarities between all these questionnaires. So the one we've looked at most isn't the one that was mentioned, but rather the Santa Barbara sense of direction scale. And it does have relationships to that. So it's not sort of tapping into a completely unrelated measure, but the calculation is basically summing up all the responses that are consistent with map use and then subtracting all the responses that are consistent with scene use or reliance on visual information while navigating. And then that difference, if it's negative, would mean that a person is more scene-based, and if it's positive, would mean that a person is more map-based. But it's a good question, and it would be important to compare it to, for example, that striatal hippocampal distinction questionnaire.
Great, thanks. Okay, next question is about your experimental paradigm. So you mentioned in your presentation using virtual reality in your experiments, and someone is wondering whether you're using an immersive VR headset to produce this experience or whether you are presenting 3D scenes on a 2D screen in front of the participants.
Yeah, so it's the latter. In the scanner especially, it would be, that's the only option available to us. But then also in our behavioral work, yeah, these are all desktop virtual reality environments, yeah.
Great, thanks. Okay, next question. Someone is saying, super cool finding regarding the turns in navigation. Do you think that the effects are due to the magnitude of change in the vista space when making a 90-degree turn? In other words, do you think that this effect scales with the turn angle?
Oh, that's a great question. I didn't think of it as a sort of continuous measure, as in, so if you, I guess, if the idea is if you turn your head a little or turn your body a little, then the perceived change is small, and therefore the shift in the context would be small. We haven't looked at that. It would be interesting in sort of, my conceptualization has always been that turns sort of segment the route because in cities they tend to be 90-degree turns. But I think it's definitely an open question whether it's a sort of continuous measure, and once you, I guess, hit a point where the difference is large enough from your original viewpoint that you then perceive it as a brand new segment, or whether it's a sort of binary distinction where you're either on segment number 1 or segment number 2.
Sure, great, thanks. Okay, someone else is wondering about your last project. When participants navigate, did they have instructed goals? And then if not, might the individual differences in exploration patterns be a reflection of people's motivation at the time of experiment, but less a strategic difference?
Yeah, that's a good question, and it's something that we're planning to tackle in a follow-up task currently ongoing. So participants were told to look for these 8 buildings that are labeled, that they were also then asked to answer questions in the on-site pointing task that I mentioned. So presumably everyone's motivation, what the overarching motivation was to find these 8 buildings because they knew they were going to have to answer questions about them. But it's still different sort of, yeah, if people felt kind of not very exploratory on a particular day, but are usually good navigators, that's definitely a possibility. So we're trying to look at more standardized individual difference measures as they relate to navigation to try to tease apart the sort of day of motivation and performance and sort of trait individual differences.
Gotcha. Thanks. Okay, I think we have time for one last question. So Fred Kiffer is asking, for individuals with higher roaming entropy, did they still explore the familiar or more commonly explored area of the environment for just as long as individuals with lower roaming entropy? Asking as consolidation is an important aspect of spatial learning. If not, why do you think this could be?
So if I understand the question correctly, it's if participants who had low roaming entropy, were they just kind of more in the periphery of the environment? Or if they were exploring, sorry, would you mind repeating just the first part?
Sure. So they're asking individuals with higher roaming entropy whether they explore this familiar or commonly explored areas of the environment. So assuming that the individuals with low roaming entropy are sort of sticking to a central location, whether those with higher entropy are exploring those as much or whether they're like exclusively exploring other regions.
Yeah, that's a great question. I haven't divided it into, I haven't looked at the sort of interplay between those two. And it would be important to test whether, whether low entropy is a reflection of just sort of being in the periphery of the environment more, or whether people have similar tendencies for the center, but then the ones with higher roaming entropy also explore more of the surround.
Gotcha. Great. Thank you. Well, thank you so much for this talk. It was really, really enjoyable. We loved hearing about your work. You're getting a ton of praise in the chat. So when you do have a chance, you should go check it out. And then also for the rest of the attendees, we are hosting a trainee-only discussion section with Iva immediately following this talk. We are going to be in a separate Zoom location so that we can all be in the same Zoom room. I will post that to the chat now. And so we will be hopping over there as soon as we log off here, and it'll be going until 2 o'clock. So feel free to bring your questions about Iva's science or anything related and beyond. But yeah, again, thank you so much. It was a really excellent talk.
Thank you. This was really wonderful and excellent questions. And thanks again for the invite.